the most recent of all of them is actually the quantum model. The quantum model, I told you, is very complicated. It deals with a lot of math-based calculations, so we aren't going to deal with it a ton, but I do want to expose you to it today so that you understand where these letters are coming from. And it's also important at its core because the Bohr model tries to tell you that you know exactly where any electrons are at any one time. And I want you to realize that's not true. Number one, we can't see them, and number two, they're always moving. So if we can't see them with our eyes and they're always moving, we want to try to give note to the fact that, okay, we actually don't know where they are specifically at any one time, but we can try to narrow it down using some math. So the quantum model dealt with that math and did a lot of calc-based calculations essentially to create what we call probability maps. These probability maps are like areas where it's likely, like by probability, it's more likely for you to find the electrons in that space than anywhere else, okay? And that's what we're working with today. So these probability maps have 4 letters attributed to them. There's the S probability map, P, D, and F. So we're going to use that here. Now, last year even I dove way more into quantum numbers and we actually talked about where these came from. I'm not doing that with you this year, so I'm going to give you what you need to know about them. So if you feel like there's some little bit of gaps here, that's why. It's actually because the AP curriculum took that out. So since they took that out, I took that out just so you guys don't have to deal with that then, okay? Now, when we do the SPD and F, there are visual representations of what these things actually look like, and that's what these are, okay? So we're going to look at these visual representations as a whole to see what these shapes are as we look at them, okay? So in terms of our probability maps, these are what we're looking at, and this is what I had you put in there. Now, no, you're not going to have to draw them or anything, but I want you to understand that every time we're using SPD or F, we're looking at a shape, and specifically a probability map where it's likely to find that electron. Those shaded areas are where it's likely to find, okay? Now, this is written super small, so I want you to write it next to it. You can see the little SPs, Ds, and Fs, but just so we are clear, our S is what we're looking at with the sphere, okay? There's only really one shape attributed to an S, it's a sphere, okay? P would be these 3. They kind of look like dumbbells. You've got 2 lobes of high probability compared to the rest. Technically, there's one along the x-axis, y-axis, z-axis. You're not going to need to know that or draw them, but I want you to visualize in your mind when we say P, we're thinking a different shape than we're thinking S. And then these down here are your Ds, and then at the very bottom are your Fs. Okay, so they are getting more complicated as we go from S to F by far. Okay, now each of these probability maps have the potential to hold 2 electrons. So what hopefully you're noticing is your S is going to have the smallest capacity at just 2 electrons. The P has 3 options, so we got a total of 6 available. The D has 5, so we can get up to 10. And then the F has 7, so we can get up to 14 electrons, okay? Now, I want to show you, because we've been talking about how the periodic table is laid out so strategically, there are actually blocks on the periodic table that correspond to these SPDs and Fs. So today when we make our full profile of these electrons, we can use these blocks on the periodic table to help us do that, okay? So on our periodic table, we're going to get these labeled as our next step here. When we actually label them, what we're looking at, again, is with, hang on, there we go, is where these areas are so we can use them to represent those. Now, what I will say about that on the periodic table is, for today's purpose, it's a little bit more helpful to think of helium as it being here instead of where it typically is. So if that helps you to visualize this, you can kind of make yourself a little note. It's really just with these electron configurations that sometimes helium being here is a little bit easier to wrap your mind around. But if you can just remember that it belongs as part of the S block, even though it's separated, that's fine too, okay? So the S block only has the potential of having 2 electrons, okay? There's only one option here. It can hold 2. We've got 2. So your S block is actually our first 2 groups of the periodic table. It's these 2. Those are our alkali and our alkaline earth metals. That's your S block, okay? Now, our P block, there are 3 shape options. Again, each has the potential to hold 2 electrons, so we have a total of 6. If you look over on the right side of your periodic table, ignoring helium, 1, 2, 3, 4, 5, 6, these 6 columns here, from 13 to our noble gases at 18, is our P block, okay? Again, ignoring that helium that's awkwardly at the top right now, okay? So this is our P block. Our D has the potential of, again, holding 5, each of 2, so 10, We've got an area of the periodic table, it's actually our transition metals that can hold 10. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that middle area is our D block. So our F block would be where? What do we got left? So down here, right? That's all we got. We got our lanthanides and our actinides. Now, this is really interesting, and I think this is just how this periodic table chose to represent it. I don't love when this happens, but it is what it is. If you look down here, there are 7, so we have a potential for 14. If you actually count across, there are 15 blocks here in the bottom. Sometimes periodic tables like to show you the lanthanide and the actinide, like the literal number 57 and 89 down here too, instead of just right here. I think that is what happened there. Just so you know, this is representing La and AC, which are also here. So they kind of doubled them up, okay? So bottom line, though, we're not really going to use the F block a lot because it's super complicated. Like, visually try to wrap your mind around these shapes. They're very tough, okay? So what we are going to do today is we're going to work to build our full electron profile for every single electron for an element that exists using our SP, D, and F. What you're thinking when we do this is you're thinking, okay, what can we visualize shape-wise as to where it's likely to find these electrons? Now, we're going to write notation that looks like this. You're going to start with a number out in front. That is the shell that we are looking at. So shell 1 is closest to the nucleus. Shell 2 is like outside of shell 1, then shell 3, then shell 4, okay? The next thing you're going to have is either an SPD or F. That's what you visualize. So you think S, you're like, oh, okay, a sphere, okay? P, or dumbbell-like, but again, you don't have to keep those things super straight in your mind. What looks like a power or a superscript will be the number of electrons that are in that shape, okay? Now, just to show you this, what it actually looks like with these blocks in the periodic table, please don't try to draw this or anything, but just so you can see it. So our first two groups, our alkaline or alkaline earth metals, are all spheres. But you can see the first sphere is just a sphere. But then once we get to the second shell, there's like a sphere within a sphere. And then as you keep going down, now you've got 2 spheres inside the bigger sphere, etc. Okay? You can see the D's getting pretty complicated looking. Your F's are insane, which why we won't talk about them. And your P's, more of that dumbbell shape that goes with your P block. Okay, so imagine your periodic table. These are the S block on the left, D in the middle, P on the right, F at the bottom. Okay? Now what matters is actually starting to write these out so you can see this in action. Okay? My biggest recommendation for today is that if it's not setting in the first couple, give it time. Okay? The more we write with these, the more I think it'll make sense to you. Okay? Now, our first question, we're going to deal with the very first element on the periodic table because it's always a good place to start. We're going to look at hydrogen. How do we remember from last unit how many electrons an element has? What do you use on the periodic table to help you determine that? So we did this last unit. What tells you that number of electrons? Yep. Great, the atomic number. So atomic number for hydrogen is 1. So we have 1 electron to account for. We want to tell someone by mapping it what shape it's going to be in terms of where it's most likely to be found. To do that, you're going to use, for the number out in front, like what I have as a 1 here, you're going to use the row number. So hydrogen is in the first row, or the first period of the periodic table. So we're going to write a 1. Hydrogen is in the S block, right? Because we labeled these two, the first 2 groups, as your S block. And it is the literal first one in the S block, okay? It also only has 1 electron. So this power that I'm writing above the S is how many electrons are in that place. There is only literally 1 electron at play here. So that 1 electron is living in the 1s. The 1 meaning it's closest to the nucleus, shell-wise. The S is a sphere, so it's a visual shape of it, okay? So you're envisioning, you got nucleus in the center, you got this sphere that's right outside of it, and there's 1 electron living in that space, okay? Let's move over to our next element, which is hydrogen, then helium, okay? Now remember, helium is the one that if you visualize it on the left, it might help you a little bit more for this. But now we've got 2 electrons at play. So we're still dealing with first row S block, but it's the second one in if you count left to right. So it has 2 electrons at play in that 1s. So again, we're still envisioning you got a nucleus in the center, a sphere area around it, and there's 2 electrons living there that are literally constantly moving around, okay? We're going to keep building, so we're going to do a bunch of them in a row, then we'll kind of start moving as we get the hang of it. So we're going to go to lithium next because that's atomic number 3, okay? And again, as I've said, these superscripts are how many electrons that it has. So hydrogen has 1, helium has 2. You would add them all together to get to that total, but we're only seeing 1 and 2, which we'll practice as we get to it. So lithium is next. We have 3 total electrons at play. With our 3 total electrons, we need to think about where they're mapping at. So it's like you're reading a book. You're going to start very top left corner every time with hydrogen, read across the line, go down, read across the next line, then go down and read across the next line till however far you have to get to your element. We're only doing lithium, so we're not going that far right now, okay? But we're always going to start with our hydrogen and helium, our 1s2 group. So we've got 2 electrons in the 1s, closest to the nucleus, sphere type shape, there's 2 electrons. I cannot put a third electron in there, the s can only hold 2. So now we are in the second row, S block, because we're still in that same block area over there, and there's 1 electron there, okay, versus 2 of beryllium, but there's 1 here for lithium. So you would say, okay, now move out to the second sphere that overlays the first one. So envision a sphere within a sphere, okay? So we're moving out to a bigger sphere that surrounds it. There's 1 more electron in there, okay? Now, we add together our superscripts. 2 plus 1 is 3. That is how many electrons that lithium has. So you've mapped it out completely. Okay? Moving next to it, we've got beryllium. So Be, atomic number 4. This time we're going to have 1s2, 2s2, because it's the second one in that second row of the S block. There's 2 electrons in that second S. Okay? So that sphere within a sphere, they each have 2. Okay? Now, we're going to keep moving across so we can see boron, because now we're hitting a different block, finally. We're in the P block now. So we've got atomic number 5. We already know that we can put 4 within those 2 S's, but we've got another one that we have to worry about, okay? So we've got 2 in the 1s, 2 in the 2s, but our next one is the second period P block, so 2P this time, second row, so 2, P block, so P. First one in, so 2p1, okay? So this is where the mind shaping that's happening here with these shapes starts getting complicated. You've got nucleus, sphere around that that's smaller, has 2 electrons. Bigger sphere around that also has 2 electrons, and then you're envisioning your first like dumbbell shape on top of that has an electron at play, okay? So you can see how the mental building of these shapes can get tricky, which is why you're never going to draw them. I just want you to understand that you're describing to someone shape-wise where these electrons are living and moving around, okay? So if we move over from boron next to carbon, we now have another electron to add in here. So we had 5 total electrons if we add together 2 plus 2 plus 1 for boron. Now we have 6 from the atomic number of carbon. So it's going to look pretty similar, right? Except at the end it's 2p2 because we have the second electron we're counting in for carbon. So 1s2, 2s2, 2p2 this time, okay? Now, what would happen if we did nitrogen, okay? I'm not going to write nitrogen, but what would happen if we did nitrogen? What would your configuration look like? So nitrogen's atomic number 7. It's right next to carbon. You going for it? Okay, go ahead.
Do I have to say the whole thing?
Just say the whole thing. It's not that hard.
1s2, 2s2, 2p3.
Perfect, okay? 2p3. Then oxygen would be 1s2, 2s2, 2p4, okay? You are adding in an electron every time. The P can hold up to 6, okay? So just see that with neon real quick. You'd have 1s2, 2s2, 2p6. And the reason I'm getting 6 is if you count in 1, 2, 3, 4, 5, 6. Okay, so it's got 6 in that second P. Okay? All right, let's jump down to magnesium. Here's where we're going to kind of spot do them so you can get the hang of this. Okay? So if we do magnesium, it's going to look like neon just did, right? But now we got 2 extra electrons. Neon had a total of 10. We've got 12 here. So we've got 1s2, 2s2, 2p6. Now where are our last 2 going? They're going in the 3s, second one in, so 3s2. Okay? Totaling 12 electrons, you add these superscripts. 2 plus 2 is 4, plus 6 is 10, plus 2 more is 12. That is how many electrons we need to have for magnesium. Okay? All right, let's jump over and let's do sulfur. Okay? So if we jump over to sulfur, We're adding in a few more electrons. Now we're up to 16. Okay, so we got 4 more to add in. We've got our 1s2, 2s2, 2p6, 3s2 was filled with magnesium. Then, with our last one, we are in the third row, p block, count in 1, 2, 3, 4. So we end with 3p4. Okay? Any questions so far? Okay, so we're going to keep adding these.